Welcome to the deep dive. Today we're looking at just a massive new report from Google DeepMind.
Yeah, it's a big one.
It really is, and the title is kind of a mouthful. It's called Gemini Robotics 1.5, pushing the frontier of generalist robots with advanced embodied reasoning, thinking, and motion transfer.
Right, which sounds incredibly technical, I know.
It does. But our mission for this deep dive is to break that all down. We're going to find out exactly how artificial intelligence is, making this huge leap from just living on our screens to actual operating out there in the messy physical world.
Exactly.
We're exploring how they're finally creating truly general-purpose robots, machines that can actually think before they act.
Right, and even share physical skills across completely different mechanical bodies.
Yes, and maybe most importantly, recover from their own mistakes in real time.
It really is a fundamental shift in the whole landscape of robotics. I mean, we're looking at machines that are finally developing a working model of physical reality.
And, that matters to you, the listener, because, well, if you've ever dealt with an automated system, you know that highly specific kind of frustration when something goes wrong.
Oh, absolutely.
Like a vending machine that just keeps blindly pushing a snack into the glass when it's stuck.
Yeah.
Or an automated phone menu that hangs up on you because you didn't say the exact right word.
Yeah.
We have this built-in expectation that machines are just completely rigid.
Right, they follow a script.
Exactly. They follow a script, and the second reality deviates from that script by even a fraction of an inch. The whole system just breaks down.
Which is the classic limitation of traditional automation,
Yeah.
right? It lacks what we would loosely call common sense.
Yeah.
A traditional robotic arm doesn't know how to recover from dropping an object because it doesn't actually understand what it's trying to do in the first place.
It's just following coordinates.
Exactly. It just knows it was programmed to move its motors to coordinate X, Y, and Z.
But the DeepMind paper we're looking at today outlines an architecture that actively shatters that limitation.
It really does.
So to really understand how these new robots operate, we need to look under the hood. How does this system take massive, abstract, real-world problems and break them down into manageable physical actions?
Well, it starts with this brilliant division of labor, what they call the agentic system framework.
Okay.
The researchers realized you can't just give one single piece of software the job of understanding the world and moving a metal arm at the same time, so they basically split the brain in two.
Oh, interesting.
Yeah. First, you have the orchestrator. This is powered by their Gemini Robotics-ER 1.5 model. And that ER stands for embodied reasoning.
Embodied reasoning, got it.
Right. And this is the part that handles the high-level logic, the planning. It can even use digital tools like a web browser.
Okay, let's unpack this. So the orchestrator is the big picture thinker. It's looking at the whole scenario.
Precisely. And then you have the second part, which is the action model.
Okay.
And this is powered by the Gemini Robotics 1.5 VLA, which stands for Vision Language Action. Its entire job is to translate those high-level abstract instructions from the orchestrator into low-level geometric robot actions.
So it's translating the plan into actual physics.
Exactly. To make this concrete, the paper outlines a really great test scenario. The user gives the system a command, basically pack the suitcase for a trip to London.
Oh, wow. So you give a robot a command that implies like a dozen different variables.
Right.
You've got London weather, the duration of the trip, what kind of clothing is appropriate.
Exactly. And the orchestrator, that high-level brain, takes that command and goes to work. With the user's permission, it actually checks your travel itinerary.
Wow.
It pulls a weather forecast for London, it processes that information, realizes it's going to rain during the trip, and decides, hey, you need a rain jacket.
That is wild.
And then the orchestrator turns to the action model and passes down the specific command, pack the rain jacket into the luggage.
And then the action model takes over. It looks at the room, finds the rain jacket, and figures out the exact spatial geometry and, the motor movements needed to physically reach out, grab the jacket, and put it in the suitcase.
Exactly.
It makes me think of a corporate hierarchy. You've got the orchestrator acting like the CEO.
Oh, I like that.
Right. The CEO does the market research, checks the weather, creates the strategic plan.
Oh.
But the CEO doesn't go down to the warehouse.
No, of course not.
They delegate the physical project to the action model, which is like the floor manager. The floor manager is the one who figures out the logistics, operates the forklift, and physically moves the inventory.
If we connect this to the bigger picture, this division of labor is exactly what allows the robot to function without crashing.
But I do have a question about that.
Sure.
Doesn't translating abstract high-level concepts directly into tiny, precise motor movements cause a massive computational bottleneck. I mean, if you have this incredibly complex AI model trying to read weather reports and simultaneously calculate the friction of a metal gripper on a nylon jacket, wouldn't that just freeze the system entirely?
See, that bottleneck is precisely what the two-step architecture avoids.
Oh, okay.
If you tried to make one giant monolithic model do everything from browsing the web to calculating the physics of a zipper, yeah, it would be incredibly slow and brittle.
Right.
The processing power required would just be immense. But by separating the vision language model from the vision language action model, you solve the computation problem.
Because they are tripping over each other.
Exactly. The system retains the broad general intelligence of a frontier AI model in the orchestrator, while the action model gets to operate purely as a specialized spatial expert. The CEO doesn't need to know how to drive the forklift.
And the forklift driver doesn't need to read the quarterly earnings report. That structural separation makes a lot of sense.
Right.
So the floor manager gets its specific instructions, pack the rain jacket. But the physical world is chaotic. It's not a pristine laboratory.
Not at all.
Someone might bump the table or the jacket might slip. How does the robot actually execute those instructions without breaking down the second something unexpected happens?
This is where we see one of the most significant breakthroughs in the paper. The researchers built what they call a thinking VLA.
A thinking VLA.
Yes. It essentially allows the action model to interleave its physical actions with a continuous stream of internal reasoning in natural language.
Wait, slow down. What do you mean by internal reasoning in natural language? Is the robot generating like a ChatGPT prompt for itself while it moves?
In a way, yes.
Really?
Yeah. As the model is processing visual data and generating the mathematical commands to move its motors, it is simultaneously generating text tokens. It is thinking out loud.
Wow.
It translates its visual observations and its motor plans into human language, step by step. They call it embodied thinking.
Here's where it gets really interesting, because the robot is essentially muttering to itself as it works.
Yes.
As a human user standing next to it, you can't actually read this text trace. You can see what it's planning to do right before it does it.
Which is huge.
It will output text saying, move the gripper to the left, and then it moves the gripper to the left.
Right.
If you're listening to this while doing the dishes or folding laundry, imagine if you had an app that printed out exactly what your hands were about to do next. It's like watching a person trying to assemble frustrating IKEA furniture, mumbling to themselves, okay, grab the weird little wrench, now turn the bolt on the left.
That transparency is a massive leap forward for human-robot interaction because it builds immediate trust.
Oh, for sure.
If a robot is holding a heavy object or, say, a sharp tool near you, you want to know exactly what its next move is.
Absolutely.
But beyond just transparency for us, this internal monologue allows the robot to perform unprecedented self-correction.
The visual example they included in the report perfectly illustrates this. They showed a sequence where their Apollo humanoid robot is tasked with packing objects into a white bag.
Right, the packing test.
Yeah, and its internal thought trace says it plans to pick up a purple water bottle from the table using its right hand. It moves its right arm, attempts the grasp, but the bottle slips.
It fumbles it.
Yeah, it falls out of the right hand and rolls over the table, ending up near the robot's left hand.
Now, in an older, scripted, automated system, this is a total failure state.
Game over.
Right. The script dictates the bottle is now in the right hand. It isn't. The system doesn't know what to do, so it freezes or just continues to blindly move an empty right hand toward the bag.
Right, it would just confidently drop nothing into the bag.
Exactly.
But here, the robot doesn't freeze, and it doesn't need a human to hit a reset button. Because it is constantly observing its environment and generating this stream of thought, its internal monologue instantly updates.
It sees the bottle fall.
Yes, and the text trace immediately changes to pick up the water bottle with the left hand. It just seamlessly adapts to the new reality.
And notice the underlying mechanism there. Decomposing a complex task through this thinking process massively improves performance.
Because it's taking it step by step.
Right. Instead of trying to calculate one giant mathematical trajectory from the table to the bag, which fails the moment the bottle moves, the robot translates the visual data into a language-based thought. It breaks the complex goal into a primitive skill, evaluates if it worked, and then acts again.
It also has this implicit awareness of success, which I found totally fascinating.
Yes.
In another part of that same packing test, the robot is told to pick up a yellow tennis ball. The moment it successfully grasps the ball, It doesn't pause and wait for some separate success detector program to evaluate its grip.
No, it doesn't.
Because it's continuously thinking, it just knows it has the ball. The thought trace immediately switches to the next goal, put the yellow tennis ball in the white bag.
The fluidity is remarkable. It proves that natural language reasoning can act as a stabilizing force for physical action.
So if we step back, we have a robot with a CEO brain making high-level plans and a floor manager brain with an inner monologue guiding its physical actions and correcting its own mistakes.
Exactly.
But this raises a big question. If the floor manager is learning all these specific spatial skills, does this brain only work inside one specific type of robot body? Because usually if you buy a new computer, you have to make sure the software is compatible. You can't just drop an iOS app onto an Android phone without heavily modifying it.
You're touching on the concept of hardware-software coupling, which has traditionally held robotics back for years.
Right.
But the DeepMind team addressed this through what they call motion transfer and multi-embodiment pre-training. They essentially created a universal mind that can natively control entirely different physical machines.
And they didn't just test this on slightly different models of the same arm. They tested it on 3 drastically different robots.
Very different.
You have the Aloha 2, which is a stationary dual arm setup.
Yeah.
You have the bi-arm Franca, which is a completely different robotic arm configuration entirely.
Yeah.
And then you have the Aptronic Apollo, which is a full-blown bipedal humanoid robot.
Right. It walks.
And the exact same core AI model can step into and control all of them.
What's fascinating here is the breakthrough of zero-shot skill transfer.
Zero shot.
Yeah. Zero-shot simply means the AI model can execute a task successfully on the very first try without ever being explicitly trained on that specific task for that specific robot.
That's crazy.
It learns a skill while inhabiting one robot body, and then it can flawlessly execute that same skill in a completely different robot body.
The data in the report on this is just wild.
Yeah.
The Aloha robot was able to successfully complete a task. Specifically, it was told to close the pair organizer.
Right.
It did it perfectly, even though that specific task was only ever included in the training data for the Franca robot. Aloha had never seen it before. And the Apollo humanoid was able to slide open the wardrobe door. It learned how to do that entirely by watching training data generated by the Aloha robot arms.
It's incredible.
I do have to push back here, though.
Okay.
If I learned to drive a standard sedan, that doesn't mean I magically have the muscle memory to fly a helicopter.
No, it doesn't.
So how on earth does a tabletop arm share muscle memory with a walking humanoid? I mean, they don't have the same joints, the same weight distribution, or the same reach.
That's a great analogy, and it gets to the heart of how motion transfer actually works. The training recipe doesn't just copy and paste raw motor commands from one robot to another.
Right, because then it would just break.
If it did, the humanoid would just flail its arms and fall over. Instead, the AI aligns the different physical bodies by extracting the common physics principles beneath the actions.
So it's not memorizing the angle of an elbow joint, it's learning the concept.
Exactly. It learns what friction is, what momentum is, how hinges work, and how objects relate to each other in 3D space. It creates a unified understanding of motion.
Wow.
When the humanoid approaches a wardrobe, it applies its shared conceptual understanding of what it means to pull a door open, mapping that concept to its own unique joints and motors. Furthermore, they train this universal mind at scale using a simulator called Mujoko.
The report noted over 90% of the evaluations to build this model were done in that simulator. But why use a simulator so heavily?
Because in the real world, physical robots break. Motors burn out, joints snap, and running millions of trial and error tests takes years. In a simulation, you can run thousands of tests simultaneously.
That makes sense.
The historical problem, however, is the sim-to-real gap. The physics of a virtual apple sliding across a virtual table rarely perfectly match the friction of a real apple on a real table. What DeepMind did was rigorously align the virtual physics in Mujoko with the real world, so the AI could learn these universal concepts of motion at a massive scale before it ever touched a piece of real metal.
But the paper does point out a limitation there, doesn't it? It's not a magical fix for every body type immediately.
Correct. We have to acknowledge the nuance. While motion transfer is a huge leap, the embodiment gap is still a real hurdle.
Right.
Moving from a sedan to an SUV is one thing, moving to a helicopter is another. A tabletop arm and a bipedal humanoid are structurally vastly different.
Yeah, completely different physics.
Exactly. The researchers noted that while the humanoid benefited from the shared learning, it still required external data specific to its body type to get a real performance boost, simply because its balance and gravity requirements are so uniquely complex.
So if this universal mind can jump from an arm to a humanoid, and if it's applying conceptual physics rather than just memorized movements, its fundamental grasp of reality has to be flawless. Otherwise, it would just crush a coffee cup when it switches to a stronger robot body.
Yeah.
How exactly does this AI see and understand its environment?
This is where we dive into the state-of-the-art embodied reasoning capabilities of that high-level orchestrator, the GR-ER 1.5 model. It isn't just looking at a flat grid of pixels. It is deeply parsing the geometry of the messy real world.
They demonstrated this with a feature called complex pointing.
Yeah.
The AI can basically overlay lightweight digital points onto its visual feed to trace a complex motion trajectory. For example, if it needs to close a laptop, it doesn't just identify the laptop and smash its hand downward.
Right, which would be bad.
Very bad. It visually draws a precise 5-point path in 3D space for the robot arm to follow, ensuring it gently pushes the screen down along its natural hinge.
What is just brilliant.
And this isn't just for sterile lab environments with white walls. They fed the model an image of a completely messy, disorganized real-world inventory shelf. The AI was able to instantly parse all those random objects, understand their spatial relationship to one another, and organize them into a clean HTML table.
It's an incredibly advanced level of semantic and spatial reasoning. But where the mechanism becomes truly impressive is in its progress, understanding, and success detection.
Right. The example they used was a robot tasked with moving an orange pack of biscuits from the basket onto the shelf next to the blue bowl.
A very specific task.
Extremely specific.
Mhm.
The AI doesn't just view this as a binary done or not done. It can predict task completion percentages step by step. And it handles multi-view success detection seamlessly.
Yes.
If one camera's view of the shelf is blocked by the robot's own arm, the AI stitches together the angles from different cameras around the room to mathematically figure out if those biscuits actually made it next to the blue bowl.
And its ability to synthesize visual geometry with deductive logic is remarkable. Consider how it handles ambiguous real-world instruments, like the analog gauge example.
Oh, we have to talk about the temperature gauge. If you're listening, picture an old-school analog temperature dial with a physical needle. It's not a digital screen outputting a clean number. In the test, the needle was pointing to a spot on the dial that had absolutely no numbers written on it.
A traditional system fails here because it can't read text that isn't there.
Exactly.
But the orchestrator logically worked it out step by step.
Exactly. The AI noted that the major numbered markings on the dial were 50 and 80 degrees Fahrenheit. It reasoned that the interval between 50 and 80 is 30 degrees.
Okay.
Then it looked at the physical space between those numbers and saw there were 2 unnumbered tick marks dividing that space into 3 equal sections. It did the math. 30 divided by 3 is 10. So each section represents 10 degrees.
Right.
It looked at the needle again, saw it was resting exactly on the first tick mark past the 50, and deduced that 50 plus 10 is 60. It correctly read the gauge as 60 degrees Fahrenheit, purely through visual logic.
Which is exactly the HOW of this technology. A vision language model maps the spatial relationships of pixels where the needle is relative to the tick marks and connects that geometry to its vast database of mathematical logic. It's synthesizing visual space with deductive reasoning.
So what does this all mean? To me, it synthesizes everything we've been talking about. We have finally crossed the barrier where AI is no longer just a text generator stuck inside a chat window on your browser.
It really is.
It is becoming a spatial expert. It understands 3D space, it understands the passage of time, and it understands physical consequences. It knows how the physical world operates.
This raises an important question, however, regarding latency. Because understanding the world accurately is one thing, understanding it fast enough to act is entirely another.
Oh, true.
Gravity doesn't wait for a processor to finish its math.
That's a great point. How fast is the system actually thinking?
The DeepMind team actually tested what happens when the robot has to figure out if it succeeded in real time while the clock is ticking versus just analyzing the video footage after the fact.
Okay.
When running in real time at 5 Hz, they found that inference latency becomes a massive challenge.
Let's break down what 5 Hz actually means in this context for the listener. That means the system is processing the world and making a decision 5 times per second.
Right.
Which sounds fast to a human, but reality is moving much faster.
Exactly. Imagine a glass slipping from a gripper. The robot has to visually register the slip, generate the text token glass is slipping, calculate the new motor trajectory, and send the signal to the metal arm.
All in milliseconds.
Yeah. If it's only updating its understanding 5 times a second, those milliseconds matter. A success prediction or a correction that takes too long to generate becomes stale data. The glass is already on the floor.
It's useless at that point.
Exactly. Solving that latency, speeding up the thought process so it matches the speed of physical reality is the next great hurdle for real-time physical agents.
It's the difference between having the reflexes to catch a falling glass
Yeah,
and just realizing, a second too late, that the glass is shattered.
spot on.
But the fact that researchers are already brushing up against these latency boundaries is incredible. We are watching the birth of true, adaptable physical agents. To wrap up our deep dive today, let's look at the major leaps forward we've covered from this DeepMind report.
Sounds good.
First, we explored a dual architecture that perfectly separates high-level strategic planning from low-level physical action, avoiding the computational bottleneck.
Second, they've introduced embodied thinking. By interleaving actions with an internal natural language monologue, robots can now self-correct and adapt to messy real-world mistakes on the fly without needing a human to hit reset.
And third, motion transfer, which allows these AI minds to extract common physics principles and share physical skills across completely different mechanical bodies, from tabletop robotic arms to walking bipedal humanoids.
Yeah.
The AI revolution is officially stepping out of the cloud. It's getting ready to walk into our living rooms, our warehouses, and our factory floors.
It represents a paradigm shift in how we will live alongside and interact with machines in our daily environments.
Absolutely. And as we finish up today's deep dive, I want to leave you with a thought to mull over on your own. We've seen today how robots can seamlessly share physical skills and muscle memory across entirely different mechanical bodies through motion transfer.
Right.
The AI learns the physics of a task and ports it to a new frame. So if an AI can extract the physical concepts of motion, could we one day use a similar system to capture and digitize a human's physical expertise?
Oh, wow.
Could we capture a master chef's exact chopping technique or a surgeon's lifetime of precise hand movements and instantly download that human physical skill directly into any robot's brain?
Now that is a fascinating implication for the future of work.
Something to think about next time you're chopping vegetables. Thanks for joining us, and we'll catch you on the next deep dive.